Okay, everybody, this is Calc 1 Day 17, Chapter 5, Section 3. So, this one is actually going to be a shorter section. I thought it would be a little bit longer when I was looking at the topics, but it's actually not too bad. And if you got a handle on the last section, this is just kind of a spin-off from it. So, now we have volumes by using cylindrical shells, and the idea here is that we have this function, and then this function spins around the y-axis, and as it spins around the y-axis, you could break it down in spots to the radius of the outside minus the radius of the inside would give you this portion here that is your delta R. And if you do that, then it has been proven that you can simplify your formula to be your 2 pi RH. What is that? Circumference, height, and then times your width. So 2 pi RH times your width would give you your volume. Now the interesting part here is that the radius is the difference between the inside or the outside radius and the inside radius. So you can see here if we have pi r squared h minus pi r squared, the first radius h, then if we factor out that pi h, we can see that the differences between the two radius, if we just multiply that by the difference, then we will then get our value. So if we know this width, this delta r, that'll give us our difference of our radius, and then we don't have to go through taking the outside circle minus the inside circle, because we will have already done that. So again, the volume when we're talking about using cylindrical cells is that we have 2 pi r, which you should recognize as a circumference, times the height times the thickness. Okay, and that would be the difference between the radii. Okay, so here is the picture that we want to take a look at now. We have some f of x, which starts at A and ends at B. Okay, some f of x that starts at A and ends at B. Then we start spinning this around the y-axis. And when we do, we get this real interesting looking figure here. Okay, now if we want to take a closer look at what that might look like, we can start splitting it into cylindrical shells. Okay, so let's look at one of them. If I take one cylindrical shell from one point to the next point, you can see actually I can use my concept of the rectangle to figure out what that area is. And if I take those rectangles all the way around, which you know that would mean that I'm going to have a limit as x approaches infinity of all these little rectangles going all the way around, then I would be able to find the volume. So here's another picture of what that would look like at different places. So this just has one place on the f of x. Here that might be. So what about lower, and what about higher? And then I'm spinning those all the way around from A to B. How many rectangles? Well, as I'm sure you are aware by this point, the more rectangles you have, the more accurate you're going to be. Just look at the difference between this, and finding the volume. This is much more smooth because we have a number more of the rectangles in this one versus this one. Okay, so the approximation to the volume of S is given by the sum of the volumes of these shells. So you're going to add all these shells together to get your volume. So what does that look like? The volume would equal from 1 to n, how many ever cylinders that you're going to have. The volume would be pi, 2 pi r, x sub I is your radius here, 2 pi r times your height times your thickness. Okay, 2 pi r times your height times your thickness. So we know that as n approaches infinity, we're looking at the definition of an integral. So as n approaches infinity, we're simply saying that we can take this formula and we can integrate it from a to b. So that will give us number 2, which is the volume of a solid obtaining by rotating around the y-axis. The region under the curve from a to b would be the integral from a to b of 2 pi x f of x dx. Again, to break it down, circumference, height, thickness. Now, just to explain a little further, if you took one of those cylindrical shells and you sliced it and you opened it up, look what you have here. You have a rectangular prism. Now that prism, the length is going to be your circumference once you wrap it all around. So this is your circumference times your height times your thickness. Okay, so you're actually taking a number of rectangular prisms and adding them together to get your volume. All right, let's take a look at example 1. Example 1 says, find the volume of the solid obtained by rotating about the y-axis, the region bounded by y equals 2x squared minus x cubed, and y equals 0. So here we're looking at y equals 0 is our x-axis, and then we have our function 2x squared minus x cubed. Now we are saying that we want to measure this from 0 to 2. So we have from 0 to 2 here is what this will look like. Now, interesting, before I go into the equation, if you take a look here, this is a computer generated picture of the solid that we're computing right now. So you can see as it spins, it's kind of interesting that we're going to use slices of rectangular prisms to figure out what our volume is. Okay, so from the sketch, we see that it's a typical shell that has a radius of x, circumference of 2 pi x, because remember, x in this category is our radius, so this is like our 2 pi r. Our height of 2x squared minus x cubed. So by my shell method, my volume would be 2 pi x times my height, 2x squared minus x cubed, times dx, which is my width, and then I'm going to integrate that from 0 to 2. And when I do integrate that, I will get 1/2 x to the 4th minus 1/5 x to the 5th. I'm going to bring out my 2 pi because it's my constant on the outside. I then am going to substitute in 2. If I substitute in 0, that's just 0. So I just look at substituting in my 2 value, and I will get that the volume will in fact be 16 over 5 pi. 16 over 5 pi. Not too bad. I actually think it's a little bit less complicated than the last section. And speaking of the last section, we're going to talk about one of the figures that we saw in the last section in example 2. So sometimes we know that there can be more than one way to do things, but finding the cylindrical shells might be much easier than the washer method, which is what we looked at before. and we don't have to find the coordinates or the local maximum. So however, let's take a look at this one. Find the volume of the solid by rotating about the y-axis, y equals x and y equals x squared. Now first I flip back to the last section, but it's a little bit different than the last section because they had a line about x equals -1 and they were rotating it about that. So it was much different than this problem. But with that being said, let's take a look at what we have here. Again, we're going to have our radius is going to be x, so we have 2 pi x. Our height is going to be our x minus x squared, which is the difference between the two. And then finally, my dx. So when we put it all together, from 0 to 1, we are going to measure this, 2 pi x times x minus x squared dx. Take the 2 pi on the outside, integrate what's left on the inside, substitute in my 1, and then of course 0 wipes it out, and I will get pi over 6. Pi over 6. Okay? All right. Give you a moment to look at that. Let that soak in. And then we're going to move on to example 3, which also talks about a curve we looked at in the last section. Y equals the square root of x. And again, I'll remind you that we talked in the last section about you should know what these parent functions look like. And this time we're going to take a look at the y equals the square root of x. Because in the last section, what we did was we solved it for x. And if we do that here, we will see that we have x equals my y squared. For rotation about the x-axis, the circumference would be 2 pi y. Again, for rotation about the x-axis. And then the height would be 1 minus y squared. So again, we are rotating about the x-axis here. So our volume will be 2 pi y times 1 minus y squared dy. And once I factor out my 2 pi on the outside, because it's my constant, and then multiply through my y value and integrate, I will get 2 pi times y squared over 2 minus y to the 4th over 4. Substitute in my 1 value. My 0 will wipe it out, so I just get pi over 2. Okay. Not too bad is what I say. All right. Next one. And last one for this section. Here we're going to look for the volume of a solid obtained by rotating the region bounded by x minus x squared. So here we have this parabola. And y equals 0. And the line x equals 2. So we have x equals 2 here. Here is my parabola. I'm going to spin it about x equals 2. So this is the kind of washer that I'm going to have. Now, keep in mind, I'm doing this from 0 to there, so I'm going to have these other washers out here as well. So I'm going to take a look from 0 to 1 of 2 pi times 2 minus x times x minus x squared. So again, has a radius of 2 minus x here, the circumference of 2 pi times the radius 2 minus x, and then my height, which is x minus x squared when I put it all together. Still the same formula we looked at in the other two. All right, simplify by multiplying it out. Put the 2 pi on the outside. Integrate it. Substitute my 1 in. Substitute my 0. Wipes it out. And I will get pi over 2. And believe it or not, that is it for section 5.3. So I will see you for the next and final lesson of Calc 1.